Okay, so first of all, I'm very happy to get some closure on David Hestenes' beta. I remember starting in 1965 at Arizona State University, he mentioned beta many, many times. And now I finally some closure in 2022. I'm very happy to see that, and it was very interesting talk I found out. So let me start by saying that in my talk, well, first of all, I like to dedicate my talk to the memory of Hermann Grossman because, as you'll see in my talk, I believe that, well, let me go through these opening remarks. The main purpose of my talk today is to show the deep relationships between Grossman algebras, Cayley's matrices, and Clifford geometric algebra. So mathematical history has deep roots that cast long shadows. Had I been born in 1843, instead of 1943, I could have been a student of the well-known and established mathematician, Arthur Cayley, and proven the general Cayley-Hamilton theorem with matrices in 1871, 5 years before Frobenius did in 1878. Or I could have worked with Hermann Grossman and William Clifford and proven it in his geometric algebra in 1871, instead of in my thesis in 1971. So the reason I'm talking about Cayley-Hamilton, because it was actually a key problem that I worked upon when I started working with David, which led me to reformulate linear algebra, the basis of linear algebra in my thesis. So what I'd like to show you today is what I think that Hamilton, you can see is the time period he lived, Grossman, Ausdehnungslehr, theory of extension, 2 editions, 1844 and 1862. He believed that his Grossman algebra provided a new foundation for mathematics. Well, in fact, I chose that as the title of my book, New Foundations for Mathematics, because I have the same conviction that he did, even though I wasn't aware of this quotation at the time. And Arthur Cayley, so the interesting thing about Hamilton is he proved the Cayley-Hamilton theorem using quaternions. And Arthur Cayley, in his manuscript, Theory of Matrices in 1858, gave the quote, "I have verified the theorem for 2x2 and 3x3 matrices, but I have not thought a proof necessary for n×n matrices." So, of course, William Clifford set down the rules of his geometric algebra in 1878. I like a notable quotation from him, which he says, quote, "It is wrong always, everywhere, and for anyone to believe anything upon insufficient evidence." Now, it turns out that Fernando Frobenius gave the first formal proof of Cayley-Hamilton theorem, some 25 years later in 1878, which is, okay, so you can say that I gave the first proof of Cayley-Hamilton theorem in geometric algebra in 1971 in my thesis. But it seems to me that these 19th century mathematicians did not realize a deep connection between matrix algebra. I think about a matrix as a coordinate matrix of a geometric algebra. So linear algebra could have been all done in terms of geometric algebra, and it's really an equivalent theorem, as I like to tell you, as a theory of matrix, as matrix algebra. So a lot of talk has been made about duality in these seminars, in these lectures today. So I'm not going to go through the different ways that duality, previous speakers have already talked about many of them. So what I'd like to do is show you how geometric algebra arises from 10 definitions, all based upon the idea of a null vector. A null vector is simply an algebraic quantity, call it V, such that its square is equal to 0. They are added and multiplied together over the real or complex numbers using the usual rules of matrix algebra. And they generate an algebra, which I denote by n. I think this is a fundamental quantity that should be talked about at all levels. And in fact, in David's talk, you can see how important the electron moves along the light cone, which is defined in terms of null vectors. So again, N then is an algebra generated by the set of all algebraic quantities V, which I call vectors, which have square 0. Okay, two null vectors A1 and A2 are anti-commutative if A1 times A2 plus A2 times A1 is equal to 0. A set of mutually anti-commuting null vectors, A1 to AN, are linearly independent if the product is not equal to 0. And they generate a 2 to the n dimensional Grossman algebra, which I denote by Gn over the real or complex numbers. So now, definition 4, let AI be the column vector, column matrix with 1 and AI, these are these null vectors here, for I equal to 1 to n. Okay, so now I'm going to take the right Kronecker product of these elements, generate the Grossman algebra, 1 with the basis elements, 1, A1, A2, A1 times A2. That's using the right, what I call the right directed Kronecker product. Okay, well, the general idea is that we take Gn of f equal to the right Kronecker product of A1 up to AN of these sets. Gives the order to the n column matrix of the basis. Well, if we calculate this out, we get the basis of the Grossman algebra, 2 to the n dimensional graded Grossman algebra, consisting of the scalar 1, the vectors, the null vector generators, and then bivectors, trivectors up to the n vector, A1 up to AN. Okay, so there are n things taken k at a time, k vectors in this Grossman algebra, which we denote by A1 lambda 1 to lambda k. Definition 5, a pair of non-null vectors A and B in this algebra N of null vectors generated by null vectors are said to be algebraically dual or compatible if AB times BA is equal to 1. Okay, so that's a new concept of duality, and I'm just defining a relationship between these two null vectors, which generate the two-dimensional Grossman algebra, well, two Grossman algebras. So here's a multiplication table of these basic elements. We have the null vectors A, B, which are compatible, and we have A, B, and BA. Multiply it out using those rules of matrix algebra, we get A squared is 0, A times B is just AB, A times AB is 0 because A squared is equal to 0, BA, and so on. Very simple table to remember because most of the terms are 0. In particular, notice that ABA is equal to A, and ABB is 0. And okay, the other thing to notice about this table is that AB and BA are idempotent. So you can see AB times AB is AB, BA times BA is AB, or BA. So in this case, we say that the dual of A is B, and the dual of B is A. And the double dual, of course. Okay, so let's go on to. So now in terms of this, of these two null vectors A and B, we define E equal to A plus B and F equal to A minus B. Very easy to verify that they satisfy their pseudo-Euclidean vectors orthogonally anti-commute. E squared is equal to 1 and F squared is equal to minus 1. And they define the bivector E times F because they're, okay, so I'm now writing down the nilpotent basis for the geometric algebra G11. That's the neutral, sometimes called the mother geometric algebra. I call it a root geometric algebra. G11 we can write it in terms of matrix notation. Again, assuming the usual matrix products. So we have a column vector 1A times the idempotent BA times 1B, and we get this, what I call the spectral basis of null vectors generating the geometric algebra. Okay, so now look, if we have a 2x2 real matrix, say, we can determine immediately what the geometric number is for that coordinate matrix of this geometric number, and it's just 1A. Put the BA in here, and then you have the matrix, 2x2 matrix, and 1B. Notice that G11 corresponds to BA, G12 B. That's why we write in terms of the basis, the matrix basis, and we call it the coordinate matrix of the element G in G11 as a real matrix. Well, now we just generalize that, taking A1 up to the right conical product gives you a 2D n-dimensional Grossman algebra, all in this generating algebra of null vectors n. And we take the dual or compatible Grossman algebra. Perhaps I should have named my talk geometric algebras of compatible Grossman algebras, because now we have the first Grossman algebra, 2D n-dimensional, and we have the compatible Grossman algebra generated by the left chronicle product of these same elements, except now they're written as row vectors. Bi of t is equal to 1 bi. Okay, so we have, this is the first Grossman algebra generated by the null vectors A1 to AN, and we have the compatible, okay, we say it's compatible because it satisfies this more general expression from the previous one, AIBJ plus BJAI is equal to delta IJ. So that's how we say that the Grossman algebra is generated by the null vectors B1 to Bn, and the Grossman algebra generated by A1 to AN are compatible because they satisfy this. Notice the anti-commutativity property is extremely important, as is the concept. Okay, so let's go on to definitions 7. So we're now defining the general geometric algebra GNN in terms of these two Grossman algebras, these two compatible to the n-dimensional Grossman algebras. So GNN is generated by, consider that the tensor product, generated by all these null vectors, A1 to AN and B1 up to Bn. It's all in this algebra of generated by all the null vectors. Then, so the structure of N should be very interesting to study in much more detail than I'm able to do it here. Okay, define the idempotents. UI equal to BIAI, and the primitive idempotent, U1 up to UN equal to U1 up to UN, B1A1 up to BNAN. Then we would do the same thing we did for the simple case, writing the general, given an n by n, well, to the n by to the n coordinate matrix G of real numbers, then the corresponding geometric algebra element is given by this expression. Well, rather than look at that, I'll just take the next simplest case. So here we see here G22. That's very important for the Dirac algebra, the space-time algebra. All these algebras are really can be considered in terms of different interpretations of G22. So we have the first Grossman algebra, 1A1, and then the compatible Grossman algebra on the right. And here you have the corresponding basis of null vectors for that geometric algebra. So any element in this algebra, G is, you just take the product of U1 and U2. This is the reverse. So remember, U1 was B1A1, so the reverse is just reversing the geometric product now. And we have this expression here then. So again, I will refer to my book, which I published independently. It's reference 5. Geometric algebra.
You have 10 minutes.
Okay, thank you. So let me go on then. So I'm just now defining any geometric algebra. Of course, any geometric algebra can be represented in terms of real matrices or complex matrices. So we essentially always think about a geometric algebra, a matrix, as the coordinate matrix of a geometric algebra. I'm specifying exactly how that can be determined for all geometric algebras here. So a coordinate vector then. So each EI is AI plus BI, each FJ is the difference, and we have a position vector in that geometric algebra in RPQ as this expression here. But this is important. So notice if I take GNN plus 1, all I'm doing is adding, so I'm thinking about the real numbers extended by these n Euclidean vectors, E1 to En with square 1, anti-commutative, and F1 up to n plus 1. This last one here is because we put plus 1 here. That's in this, the pseudoscalar of that algebra is in the center of the algebra, so it behaves like the square root of minus 1. So the imaginary number I can always be interpreted by adding one extra dimension to the neutral or geometric algebra GGN plus 1, and you can see the pseudo unit, well, we can write it as I times the dual, where I is just the product of all the elements in this GN plus 1. Two important examples. The only difference between these geometric algebras, G12, G11, and G3, is how we interpret the vectors, bivectors, and trivectors in those algebras. Well, of course, G11 is thinking about C being the ordinary complex numbers with I equal to square root of minus 1. So let's just see how that works. For G12, we have E1 equal to A1 plus B1, A1 minus B1, and the trivector E1 times F1, F2. Complex numbers, we do this, but I is now the square root of minus 1. G3, we're reinterpreting what's called a vector and a bivector in the algebra. So E1 is E1 plus B1. Now a second vector, E2 is I times the dual element times F1. And E3 is just also interpreted in G3 as a bivector E1, F1. Certainly this must have physical consequences which are related to the physics of quantum mechanics and everything that David was talking about. So I call root geometric algebras G11 and G12 because, well, all the other geometric algebras are constructed from those two basic geometric algebras. Okay, so I'd like to show you a slight modification of the horosphere, which has already been discussed, but which I think is important. So in our picture here, we take the real number line, just the x-axis to be RPQ. We translate it by a null vector A, and we get the affine plane of APQ. And then we have the horosphere. Let me just show you the next. You can see here, the horosphere is actually this parabola here. It's similar to the other picture, but it's a little bit different the way things work out. So again, the affine plane, position vector is x plus a. We're just translating an element in our PQ by the nilpotent A. Horosphere, notice this, it takes a simpler form than the usual form people write it as. The position vector in the horosphere is XC. We sandwich B in XA, B, XA. And you can see it's all in the larger pseudo-Euclidean space, RP plus 1, Q plus 1. So again, X is just translated. Notice that X squared these are basic relationships, but notice the usual relations. I'm not going to dwell that. They completely can be recovered one from the other. And let's see, where did I have my XC? Oh, here, I wanted to show you this. The XC is on the core sphere is 1/2 XA. And then we have, well, it comes out as XA minus X squared B, which is quite a bit simpler than the expression that you've seen earlier in other talks. So I think this is a better way of looking at the Hor sphere.
At 5
Well,
minutes.
Okay, let me just, I just want to say a little bit about Alfor's Balin matrices. Very interesting correspondence. Linear fractional transformation in geometric algebra can be expressed in terms of multiplication of matrices with RP, with the geometric numbers of GPQ in it. So here's a basic relationship between translations, inversions, dilations, and reflections. Closing remarks. After the publication of the second edition of his book in 1862, failure to get recognition for his work, Grossman turned his attention to studying Sanskrit. Perhaps I will follow his lead. I am forever grateful to the welcoming hospitality of my many Mexican, Polish colleagues and for their scientific collaboration in their beautiful and exotic countries, which I call home for many years. Thank you. So here I'm just giving references. I'd like to point out I had the opportunity in Mexico to play with a Ukrainian professional pianist, and you can, if you're interested, we were jamming just one-time performance at a party. So, but these references, I will publish my talk on my ResearchGate page at least. I'm not sure. I guess it'll be recorded on the conference too. Okay, appendix is not really important. Just to show you why, how it course. It's very simple demonstration of the relationship between a linear fractional transformation and its representation in terms of Alfor's Balin matrices. So thank you very much. And thanks to the organizers too, of course.
Are there questions in the room for Garret? Hamish, do you have a question? I see Eckhart, maybe.
Oh yeah, thank you for this beautiful talk. I wonder, basically you start with this origin infinity null vector pair of the conformal geometric algebra, and you generate the whole thing from it. Can it be said like that?
Would you please repeat your question again, Eckhart?
Basically, you start with two null vectors in the conformal geometric algebra, and they span such a space with signature 1, 1. And then you go on and generate everything from it, even the Euclidean part, basically.
Exactly. As two compatible Grossman algebras, the A's generate one compatible Grossman algebra, the B's generate the second. So the two Grossman algebras are compatible. This seems to have been missed by these 19th century mathematicians. Their times of living overlap. There's no excuse why they missed it. And of course, it set back geometric algebra 100 years, basically.
Thank you.
So you start from zilch and then build it up. Any more questions? If not, then we are all going to have some coffee. Thank you for your presentation. Let's give a final round of applause for, oh, there is one question, David says.
Oh.
On the chat.
Oh, okay.
I have a question, if you can hear me.
I can hear you.
Are you Timothy?
I am Timothy.
Okay, Mike Timothy.
Yeah, I'm not an expert in the area, but this strikes me as a lot like fermionic field theories. Have Have you anything to say about that connection, or maybe David Heston does?
Well, actually, I believe this emphasizes the structure of a matrix. It's just a new Clifford algebra or geometric algebra is just the structure of a matrix in a certain basis, because a matrix is just.
What's interesting about this is a fermionic field theory is a multi-particle theory, and that's exactly where David's work stops. So there seems to me to be a lot to be done in that direction. Just a general high-level observation.
Okay, so yeah, anti-commutativity is extremely important, and how you interpret a bivector or vector is very fluid in geometric algebra. Each observer has his own way of defining what's a vector and a bivector. Electromagnetic field is observer dependent. So
and if each observer is a separate electron, then life gets interesting.
yeah, so that's why geometric algebra is so successful in physics, because it captures the notion of anti-commutativity and symmetric and anti-symmetric, which is completely necessary in physics.
David, do you have anything to say about this? Okay, thank you.
David says, I've already said it before. Famous last words.
I know you have a paper on it.
Okay, we're running slightly late, so we're ready for coffee over here. Thank you very much for your contributions, and we're signing off for this round.